Today we're going to take a look at balancing equations. So the first thing we kind of want to focus on is why exactly do we need to balance a chemical equation? So let's take a look at this reaction to make water, where we have two atoms of hydrogen reacting with two atoms of oxygen to produce a water molecule. So if we take a look at this reaction, something seems a little off here. We have two atoms of hydrogen and two atoms of oxygen reacting, yet when we make a water molecule, we're missing an oxygen atom. Now, we all know the law of conservation of matter, that it can't be created or destroyed. So where exactly did this oxygen atom go? It can't just disappear into nothingness. So that means that if we have two oxygen atoms to begin with, which of course we do because oxygen is diatomic, then there should be two at the end. Now, if I just bring over and have a random oxygen atom on my product side, that's not exactly right because this reaction is making water. It's not making water plus an oxygen atom. In addition to the fact that, again, oxygen is diatomic, it can't really even be alone anyway. So if this reaction is making water, then in order to solve my problem of the oxygen atoms, if I want to introduce another oxygen atom, I have to do so in the form of another water molecule. So in order to have two oxygen atoms on my product side to conserve the matter, that's the equivalent of having two water molecules, because each one's going to bring one oxygen. But doing so, you can kind of see here that I've got four hydrogen atoms. Well, I had two originally, but now I've got four. This is the opposite of what we saw with the oxygen, where a random oxygen was missing. Now, all of a sudden, I have two hydrogen atoms that just randomly appeared because I had another water molecule. Of course, I can't just create these hydrogen atoms. So that means I originally needed another pair for another two. So now we could take a look and see how our number of hydrogen atoms are the same, our number of oxygen atoms are the same. Matter has been conserved here because no atoms have just appeared and disappeared in my total reaction. So in order to conserve matter, I needed two molecules of hydrogen to react with one molecule of water. Doing so produces one molecule of oxygen, and that produces two molecules of water. This is known as a balanced equation. A balanced equation is an equation where we have conserved matter, aka we are making sure that the number of atoms on both the reactant and product side are the same. We do so by changing the quantity of each substance that's involved in a reaction. So, in a balanced equation, we are always going to uphold the law of conservation of matter, where matter can't be created and it can't be destroyed. So however much you begin with has to equal the amount that you are finishing with, which means that in a chemical equation, there are equal numbers of atoms on both sides of the reactions. So however many atoms there are on the reactant side must equal the number of atoms on the product side. No more, no less. If you have an unbalanced chemical equation, where you are just listing what's reacting and what's being made, that's known as a skeletal equation. We have to balance all of our equations because of this law of conservation of matter. That is the accurate depiction of how these substances are reacting with one another. And again, the goal is to ensure that the number of atoms on both sides of the equation end up being the same. So that's why we have to balance reactions, because of this law. Now let's take a look at how exactly we balance reactions. One really important thing to kind of remember when balancing equations is the difference between a subscript and a coefficient. So we have seen plenty of chemical formula up to this point. The subscript, those tiny little numbers in the formula, indicate how many atoms are present in that substance. So if we take a look at water, H2O, this subscript, the small little 2, tells me that I've got 2 hydrogen atoms present in a molecule of water. No subscript implies 1, so I have 1 atom of oxygen. So in one water molecule, there are 2 hydrogen atoms and 1 oxygen atom, and that's what the subscript tells me. A coefficient, much like how we see in math, are the numbers that go in front of the substance. These indicate how many of each substance I have, not how much is inside of one. So going back to our water equation, this big 2, the one that's going in front of the substance, not in the substance, is telling me how much of each substance I have in my reaction. And of course, no coefficient is going to imply 1. Now, when we balance equations, we have to change the coefficients. We never ever change the subscript. If you change the subscript, you are changing what the substance is, which we cannot do. So in my reaction to make water, I have to change the coefficient, how much of each substance I have. I cannot change the subscripts, because if I change the subscripts, I will no longer have hydrogen, oxygen, or water. I will have something completely different, because I am modifying what the actual compound is, or substance is. So balancing chemical equations, it's kind of like an art form where everyone will have their own way that they want to do it. These are my kind of steps that I've kind of put together. But as you work on it, everyone kind of comes up with their own strategies. Now, I won't bore you with going through all the details here. You could just, pause and read it for yourself. But this is always how I approach balancing equations. And again, everyone will always figure out their own way. The more you do it, the more it'll kind of start to come to you with whatever method you want to use. Plus, sometimes when the equations get a little bit more difficult, it becomes more about just intuition and experience and how to approach certain things, because this method won't always work. Sometimes you have to think outside the box, and that's okay. Okay, it's to each their own here. But the one really important thing that has to be consistent between everybody is writing out the chemical equation correctly. That's why it's the first step and the most important step. If the chemical equation is written incorrectly, then you have the wrong number of atoms, which means when you go to balance it, you are equating the incorrect number of atoms to one another. Okay, so I cannot stress enough how important writing the reaction is going to be in order to balance it correctly, which means we have to be careful of diatomic elements, okay, the Brinkerhoff elements, where when they are alone, they are with a 2. They are a molecule when alone. Okay, so this is where you really want to focus on to begin with before you even balance. Just my recommendation, get comfortable with being able to write chemical equations. Really, really important first step. So I'm going to show you 2 different methods to balancing a chemical equation. One is more of a mathematical approach, just using numbers. The other one's better for visual learners, which I actually kind of diagram how to balance an equation. So let's take a look at this first reaction of iron with oxygen producing iron 3 oxide. So my first method, I'm going to use numbers. This is a better approach for those who like math. So for me, I generally like to write my elements underneath the arrow, which is less work and I can work on both sides at the same time. So I'm going to list out all the different elements in the reaction. So in this reaction, I've got iron and I've got oxygen. Then I want to tally both the number of atoms on both sides for each element. On the reactant side, I have 1 iron. On the product side, I have 2. For oxygen, I have 2 reactant atoms and I have 3 product atoms. So generally speaking, when I balance an equation, I typically look for the lowest common multiple between the 2 numbers. So in the case of iron, I have 1 and 2. Their lowest common multiple is 2. I need to make them the same, which is the whole point of balancing. So in order to make my 1 into a 2, I must double it, which means in my equation, I will need 2 times as many irons. And again, I'm putting this as the coefficient because this is going to adjust the number of iron atoms I'm going to have. If I put it as a subscript, I'm changing the substance, which we can't do. So by doubling my irons, I now have an equivalent amount. My irons have been balanced. So let's take a look at oxygen. I have 2 oxygens on the product side, 2 on the reactant side, 3 on the product side. In order to get them the same, the lowest common multiple is 6 between them. So in order to go from 2 to 6, I must triple the number of oxygens that I have. Now in order to go from 3 to 6, I am doubling it. Now if you notice here, the oxygen is actually in a compound. So I can't just put a 2 and break up this compound. If I want to double the oxygens, I'm going to need double of everything, because that's where the oxygen is located. Now, my oxygens are balanced, but when I doubled the product, the oxygen is in a compound that also contains iron. So doubling the number of oxygens also doubled the number of irons. So I no longer have 2 product irons. I have 2 times 2. I have 4. So now, although my oxygens are balanced, my irons are no longer. And that's okay. Sometimes when you balance one element, it will affect the amount of another. It is just part of the process. So here my irons are unbalanced. I've got 2 and 4. I need to make them the same. So lowest common multiple between 2 and 4 are 4. So this original coefficient that I had for iron of 2 was actually incorrect. The correct coefficient is going to be 4. Sometimes when you put a coefficient, it'll change, and that's okay. All that matters is not what's happening during the process, but what you finish with at the end. So now all of my atoms are balanced. I have 4 irons on both sides, 6 oxygens. My coefficients of the reaction are 4, 3, and 2. I cannot simplify 4, 3, and 2, and so this is my final balanced equation. So taking a look at another method to balance. This way is a little bit easier for those visual learners who actually like to see the quantities changing so that they can go ahead and adjust it without having to worry about multiplying and adding and all these numbers. I call this method my shape method. In this shape method, we actually diagram these atoms. That way you can actually see how they're going to balance out or equal out to one another. So I use different shapes to represent different elements. So in my shape method, I'm going to designate iron as being a circle. So if I have 1 iron atom, I'm going to have just 1 circle. I'm going to use triangle to represent my oxygens. So I have 2 oxygen atoms, and so I'm going to draw 2 triangles, and I'm going to make sure they're touching. That way this is implying that they are bonded together. On the arrow, I'm just going to draw a little fence between them. Now for the product side, I have 2 irons bonded with 3 oxygens. Since circle is my iron and triangle is my oxygen, I want to show that I have 2 irons and 3 oxygens. And again, I'm just going to try to make sure that they're touching to imply that they're bonded. So right now you can see that we have 1 iron, 2 oxygens, and then a compound containing 2 irons and 3 oxygens. The whole goal again is to make sure that both sides are the same. So currently I have 1 circle on the left side, 2 circles on the right side. In order to make them the same, I will need another circle. My circles are now balanced. So now let's work on the triangles. I've got 2 triangles on the left, 3 on the right. So in order to make them the same, you would think, okay, just add 1 triangle and we're done. We have 3 on 3. But we can't do that, because on the left-hand side, triangles come in pairs. So I can't just add a single one. I must add 2 of them at a time. But now I've got two triangles on the left side and three on the right. Sorry, four triangles on the left and three on the right. So we have to make them the same. Let's go ahead and add one more to my right side. But on the right side, triangles don't come by themselves. They come attached to all this other stuff. So I have to repeat the entire sequence of three triangles and two circles together. Okay, but now I've got six triangles. And I've only got four on the left side. Well, triangles come in pairs on the left side, so let's go ahead and add some more. And we'll keep going back and forth until they end up being the same. So adding this extra pair has now equaled my triangles. I've got 6 on the left, 6 on the right. Now going back to circle, I have 2 circles on the left and 4 on the right. Well, circles can come individually on the left, so I'll just add 2 more to equal them out. So now my circles are equal on both sides, so are my triangles. So all I gotta do now is just count how many groups I've got. So for my iron group, I've got 1, 2, 3, 4. For oxygen, I've got 1, 2, 3. And then for this iron 3 oxide, I've got 1, 2. So there's my balanced equation. 4, 3, 2. It's the same exact outcome that we saw when we actually calculated these numbers with math. But in this approach, you can actually see the different atoms represented with shapes and just keep adjusting the quantities. As long as you're consistently repeating the patterns, you can go ahead and actually keep changing the quantities until you visually see that they're the same. So however you like to balance equations doesn't really matter. Everyone will have their own approach, but we have to balance all of them to make sure that matter has been conserved.